In this video, we're going to take a look at the second of the two comparison tests for series, and that is the limit comparison test. And just like with integrals, it's going to work very similar, but we're going to see a few slightly different elements, and we'll see that as we go forward. So let the series an and bn be two series such that an is greater than 0, bn is also greater than 0, but this time we don't have any true inequality between them. And those two facts that it has to be greater than 0 has to be true for some n little n greater than big N, where that big N should be a big N right here, is just some integer. Meaning at some point, these two sequences become positive. And the reason it's at some point is, remember, we can always just pull off those first n sequences, those n terms of the sequence, add them separately, and then whatever the back end's doing, if it converges, great, it clearly converges. If it diverges, it diverges. So that's why it's just for some n large enough. So then, if the limit as n goes to infinity of the ratio of an over bn is equal to L, where L is between 0 and infinity, then an and bn, the series, both converge or both diverge. That is the same as our integral limit comparison test. The limit as n goes to infinity of that ratio an to bn is equal to 0, and bn, the series bn, converges. So too does the series an. And if we take the limit of the ratio an to bn, if that goes to infinity and bn diverges, so too does an. So we can correct that. Made a mistake on about every line there. So I've got them all fixed now. So again, if the limit of the ratio is going to infinity, if the bn diverges, so too does the an. So before the limit comparison test said it really didn't matter which one we called the n and which one the bn was. Again, we have some flexibility. We could name the an original and bn the one we're comparing it to. It doesn't completely matter, but do notice that if we don't get that limit value between 0 and infinity, well, the bn informs what the an does. So for that reason, the thing that I'm creating to compare to, I like to call that the bn, because again, if we get the 0 and infinity, if we let the bn be the thing we started with, it doesn't tell us anything. So I'm going to consistently set my comparison to be the bn. And just to talk through these rules for a second, the first one again makes sense. It's exactly what we saw before. The reason these second and third ones are working, well, think about it. If we know that the bn is converging, meaning it's going to a set value, and the an is, if we're still getting 0 out of that an is not going to be allowed to blow up. If we have a convergent series value, so we're getting something like 5 down here after we add up all those sequence values, well, then the numerator's going to have to go to a set value smaller than that to get to 0. That's the only way that's possible. So that makes sense. If the bn is converging, well, the only way we're going to get to 0 is if the numerator is going to a smaller value faster. Then if the denominator is diverging, if the numerator was converging, well, that would just be going to 0. If we have something like 5 over infinity, that would be going to 0. So the only way this limit goes to infinity is if the numerator is going to infinity faster than the denominator. So I think rules 2 and 3 kind of make sense here. Okay, so let's take a look at an example. Here we have a series. We'll determine if it converges or diverges. N is equal to 1 to infinity. And notice that we don't have a series that is always larger than 0, because if we were to plug in the n equals 1, 3 minus 4 is a negative value. But again, we just need it to be true for some n large enough. And so 5 over 3n minus 4n, 3 to the n minus 4n, is greater than 0 for n greater than 1, meaning greater than or equal to 2. So it is positive for a large enough value. Now we're going to have to choose something we want to compare to that we know what it's doing. So I think there's two obvious choices here. One would be 1 over n. We clearly see that there's a constant over an n, and so 1 over n might be a useful comparison. The other I see is a 1 over 3 to the n, and again, that might be a useful comparison because we see that 3 to the n, so kind of the two variable expressions. Now, similar to what we did with the direct comparison test, I'm going to try and make an assumption here to start with. I'm going to make a guess as to whether I think it's going to converge or diverge, and I think it's going to converge because that 3 to the n is going to be the driving force. The 4 to the n, 4 times n rather, is going to, of course, vary, is going to change, but not as quickly as that 3 to the n. So I'm going to compare. I'm going to set my bn to be equal to 1 over 3 to the n. You could say, well, couldn't it be 5 over 3 to the n? Sure, but I don't really need it to be. So that's obviously going to be greater than 0 for all n. So now let's take the limit as n goes to infinity of the an 5 over 3 to the n minus 4 times n over 1 over 3 to the n. So when we do this, we can multiply by the reciprocal. We're going to get the limit as n goes to infinity of 3 to the n over times 5. Can't forget that 5 times 3 to the n minus 4 times n. So if we plug in the infinity right now, we get infinity over infinity, and so we have some options here. I think you could divide out by the 3 to the n, or we could apply L'Hopital's rule. That might be the most direct to see what's going on. So if I apply L'Hopital's rule, 5 will be a constant multiple. We'll have times 3 to the n times the natural log of 3 over, we'll have the 3 to the n times the natural log of 3 minus 4. And that's still going to infinity over infinity. So I'm going to apply L'Hopital's again. And what we see is that we have the 5 times 3 to the n. Now we have a natural log of 3 squared. It's there twice. Over 3 to the n times the natural log of 3 squared. The 4 is gone. Notice a lot of things are canceling. So we're left with a limit value of 5. Again, I think we could have probably looked at it in the very first step and seen that this is going to go to 5 as that eventually is going to disappear. So don't necessarily have to show me all the steps of L'Hopital's, but we need to convince ourselves that the limit is equal to some number. In this case, the limit is equal to 5. So remember that because the limit is equal to 5, that tells us that we have this 1 over 3 to the n power works for our limit comparison test. We get a limit value between 0 and infinity, so they will do the same thing. So now we can think about what the series 1 over 3 to the n is doing. Just write that a different way. Well, that should be standing out to us as our geometric series is a convergent geometric series. The r is less than 1, since the limit of, as n goes to infinity, of our 5 over 3 to the n minus 4 to the n times n, keep doing that, over 1 over 3 to the n, since that limit is equal to 5, the limit comparison test, which I'll abbreviate LCT, tells us the two series do the same thing. The two series both converge. Thus, the series we start with, series n equals 1 to infinity of 5 over 3 to the n minus 4 to the n, 4 times n. My goodness, my pen's not working. 4 times n converges. Okay, and so there we have it. Now, one thing I should have specified during the direct comparison test too, and I didn't, I'll specify it now. Notice we're comparing to a geometric series. We know that geometric series converges. We could actually find the value of convergence. We could find the sum of this series. When we're applying that direct comparison test, that is absolutely meaningless, because just because we know where this converges does not mean that our thing converges to the same point. Clearly, we're changing the numbers. And so yes, both things are doing the same thing. They are both converging. But just because we know where this geometric series converges to doesn't mean that ours is converging to the same point. So the direct comparison test, limit comparison test are only going to show convergence or divergence. It's not going to show us where they're going to. I do want to point out too that, again, I said that sometimes the limit comparison test, direct comparison test, either could be used. If we think about that direct comparison test, well, probably I would have wanted to compare it to 3 to the n. And because it's converging, we would want that to be larger than 5 over 3 to the n minus 4 times n. And the problem, though, is if I make the denominator smaller, I'm making the fraction as a whole larger. So this is a false inequality, and that's why this one's just a little bit more complex to apply a direct comparison test. Now, does that mean that we couldn't have applied the direct comparison test? Could we have found something to compare it to? I'm sure we could have, but why stress ourselves out like that? Why do all that extra work when the limit comparison test gave us a way to just compare to the thing we wanted to right away without having to do any work on figuring out, okay, is it smaller or bigger? What is it doing? Now this next one, example 2, the series n equals 6 to infinity, that one should look familiar if you watch the direct comparison test video because it has the same example 2 as before. This is a good example where we can use either test. And so here we can apply the direct comparison test. I'm going to do the limit comparison on this video. And just like before, we know that this 3 over n minus 5 is greater than 0 for n greater than 5, which obviously we have, n is 6. I'm going to compare it to 1 over n. I could have compared it to 3 over n like I did before, which is also greater than 0 for all n greater than 0. So our conditions are met. So now I'm going to go ahead and apply the limit. So the limit as n goes to infinity of 3 over n minus 5 over 1 over n gives us the limit as n goes to infinity of n over 3n, because I multiply that 3 to the n, over n minus 5. I'm just multiplying by the reciprocal here. And so again, if you want to use L'Hopital's rule, you can do that, or you can divide by the n. There's a number of ways to get this limit. We're going to get the limit value of 3. And same as the last example, because we're getting a limit value between 0 and infinity, that tells us the two series are doing the same thing. We know the series n equals 1 to infinity, 1 over n, diverges as it is a harmonic series since limit n goes to infinity of 3 over n minus 5 over 1 over n is equal to 3. The limit comparison test tells us both series diverge. Thus, the series n equals 1 as 6 to infinity of 3 over n minus 5 diverges. And just like in the previous video, the reason I started with an n equals 6, so we avoid that discontinuity at 5. So we have a divergent series here. Let's take another example, one last example. The series n equals 1 to infinity of the natural log of n plus 5 over n. And we're going to apply the limit comparison test. And so what's kind of jumping out off the paper at me is the fact that I again have that 1 over n. Now we do have natural log of n in there as well, so that could be causing some trouble, but still that's going to be increasing at a rate slower than the n. So I think I can probably compare it to the 1 over n. We'll see. But just like with number 1, it would be much harder to use the direct comparison test here because adding natural log of n to 5 is going to be a bigger number. So actually I take that back. It wouldn't be all that hard to use the direct comparison test here, but let's apply the limit comparison test. So we know that the natural log of n plus 5 over n is greater than 0. I'm going to compare it to, I believe, 1 over n, which is greater than 0. Again, stating the conditions are true. Limit as n goes to infinity of the natural log of n plus 5 over 1 over n. And so we'd get n times the natural log of n plus, I left something off there, sorry, natural log of n plus 5 over n, which is the original sequence, and then over 1 over n. And so then I multiply that n to the numerator, and I'd have this expression right here. The n's are both canceling, and so this limit is going to infinity. So this is one of those cases 2, 3, which is a little bit new, says, okay, just because we don't get a limit value doesn't mean that all hope is lost. Now we get to look at that bn, and whatever it's doing tells us what this thing is doing. So because the series n equals 1 to infinity, 1 over n, diverges because it's all harmonic series. Okay, so now we are going to take our limit as n goes to infinity of the natural log of n plus 5 over n, all over 1 over n. So we multiply the n to the numerator, natural log of n plus 5, all over n. The n's cancel. So what do we see? I'll drop my limit. We see as we take the limit, as n goes to infinity, this thing is going to infinity. So this is one of our cases 2 and 3. It doesn't tell us all hope is lost. We're just going to have to think about what the bn is doing. And luckily, by setting our bn to be the function that we created, that we know exactly know what it's doing, we can state what our original series is doing. So we know 1 over n, the series n equals 1 to infinity, is a divergent harmonic series. Thus, since the limit as n goes to infinity of the natural log of n plus 5 over n over 1 over n is equal to infinity, the limit comparison test tells us that the series n equals 1 to infinity, natural log of n plus 5 over n also diverges. And there we have it. We have shown the divergence of this series. Very, very similar direct and limit comparison test to what we were doing before. We are just applying it now with our series ideas. Keys to remember: we've got to show conditions are met. So we've got to show those series are positive. We've got to show those limit values are going to the appropriate thing. In the case of the direct comparison test, again, showing both series are positive, but also that inequality has to hold true. So different times we might want to use one or the other. If it's just a lot going on with this series, if there's just a lot of moving pieces, say for instance, if I have the series n equals 1 to infinity of 5n cubed plus 3n to the 5th minus 2 over n to the 6th plus 3n squared plus n. There's a lot of pluses and minuses. I just don't want to have to weed through that to figure out what's bigger, what's smaller. That's a great candidate for the limit comparison test. If there's inequalities, we just can't get them to fit. If we're subtracting or adding things in the wrong spots and we can't get those inequalities to fit, limit comparison test, probably a better option. If we have those trig functions, sine and cosine, well, they're always bound between -1 and 1. That's a great candidate for the direct comparison test. So again, we can use the two interchangeably in a lot of cases. One or the other might be easier.